Good evening and very warm welcome to the Oxford Martin School. I'm Ian Goldin, I'm the director, and it's a great pleasure to see you all here, and particularly to welcome Lillian Martin, who's with us this evening, the widow of our benefactor, James Martin. I'm delighted this evening to be able to introduce Chris Lintott. He's the University Professor of Astrophysics. He was also the co-director of the Oxford Martin program on computational cosmology. As many of you know, the Oxford Martin School is dedicated to solving the problems of the 21st century. And when the computational cosmologists came to us and said they wanted to be part of the school, my immediate reaction was that we don't do billion-year extinction cycles. We're more interested in the next decades. But they convinced me that they are doing work which will affect our futures in our lifetimes, that will impact because of the sorts of technologies and techniques that they're developing and the knowledge they're gaining on all of our lives. And indeed, Chris's work with his colleagues on Galaxy Zoo, the Zooniverse, and other projects are, I think, the best example of citizen science, big data analytics, etc. And many of the learnings from those projects are being applied in climate science, in health, in biodiversity, and many other areas already. So we've already seen a lot of cross-learning from this. Chris is not only a leading scientist, he's also very good at engaging citizens and popularizing science, which is so urgently needed in many dimensions. Some of you might recognize him as the new Patrick Moore from The Sky at Night. And of course, with Patrick and Brian May, formerly of Queen, I guess still of Queen because they occasionally play together, he has done 2 books. So he's, I'm sure, someone that's very well known to you in many respects, and he's going to help us understand something which seemed absolutely front page news a few months ago, Philae, the Comet, and its journey. It's no longer in the news, but it's still very much something which I'm sure we are very keen to have. So, Chris, welcome. You have the floor.
Thank you. Thanks, Ian. It's always a pleasure to speak at the Martin School, and it's great to see so many of you here. I'm tempted to take credit for that, but I actually think it's an indication of the interest that this mission created. It really grabbed the attention of the world because it was an adventure, and that's what I wanted to emphasize in my title. This really did feel like a scientific adventure. I want to emphasize 2 things at the start. One is that I think this story, the story of a team of a few hundred people from across Europe and indeed across the world who came together to collaborate on a problem that took many decades to solve, I think is something that can help us with the core mission of the Martin School, because this is an international long-term collaboration to achieve something very difficult, and I think there are lessons there. The second thing is that I'm not speaking from a position of expertise at all. I am a fan of this mission, as I hope many of you are. I can see at least a couple of people in the audience who know much more than I do, so I hope they'll interrupt me or speak at the end. But it was a privilege to be there. I was at mission control for the few days that Filet operated, starting with this dramatic descent. What you're seeing here are images of the Filet lander as seen from the Rosetta mothership as it descended down towards the surface of the comet. Now, just to illustrate my position in this, I said I was a fan. This is mission control not Houston, but Darmstadt, which has a slightly less sonorous ring to it, but nonetheless is run with Teutonic efficiency, as you'd expect. This is the place that you saw on the news. It should be pointed out that this is only used for special events. The real mission control is an office upstairs with 3 computers in it. But when they need more people and space to think, they use this larger one. And I asked one of the team what they thought of being in the big control room, and they complained that the coffee wasn't as good, and they were looking forward to getting back to their computer upstairs. So designing for personnel is important even on space missions. This is actually taken a few moments before contact with the lander was lost. I am one of the blobs sitting back here. safely outside mission controls. So I want to emphasize that none of this was, I can take credit for none of what I'm going to be talking about. I was a mere observer. But people have been observing comets as celestial phenomena for as long as humanity has been looking to the skies. And there are lots of famous historical examples of how comets have entered into our folklore and our consciousness. I thought I might mention this. This is a painting from the painter Giotto. This is the Adoration of the Magi, and the orange thing at the top is Halley's comet, which he'd observed in 1301 on a return, and was so impressed by its spectacular appearance in the sky that it stands in here for the Star of Bethlehem. I leave to my theological colleagues the decision as to whether that's a sensible attribution or not. I got into trouble in the Times for commenting on such things, and 3 Oxford theologians wrote in to correct me, so we can discuss that later. However, what I like about this painting is that it shows the fundamental morphology, the shape of the comet. There's a nucleus at the center of a coma, an extended atmosphere, the round blob, and then there's a long tail stretching out into space. And Giotto has in fact captured a sort of astronomical impression of what he must have seen. And most comets follow that basic structure. In recent weeks and months, we've had a reasonably nice comet. This is a comet called Comet Lovejoy, named not after the TV character, but after its discoverer. And Lovejoy was just about bright enough to be seen with the naked eye from the center of Oxford. I don't know, how many of you, did any of you see it? A few people. This is a way of identifying the amateur astronomers in the room. This is good, well done. And again, you see a nucleus that's obscured by this coma and a long tail stretching off into the distance. In this case, a rather scraggly, ill-defined tail. The color's significant as well. This isn't just image processing. That greenish color is because the light that we're seeing from Lovejoy comes from molecules, from complex chemistry in and around the comet's nucleus. In this case, it's actually nitrogen chemistry. It's primarily CN, a molecule of carbon and nitrogen that's glowing there and giving off that color. And so chemistry is going to be a big part of our story as well. Comets aren't just about physics and engineering. They're essentially a chemical story as well. Now, how do they get this distinctive shape? For most of the time, a comet's nucleus is presumably an inert body, mostly ice and dust, as we'll see in a second. But as they come in towards the inner solar system, they're heated, gas starts to be given off in this to produce the coma, and then that material is swept backwards by the solar wind, by particles streaming away from the sun. And what's nice is if you look at the right place, we can see this happen. So this is an image, or a series of images from a spacecraft called Stereo. You can see there's a little comet up there in the middle. It's not the most distinct image in the world, but there's a little blob. That's Comet Encke, a regular visitor to the solar system. And if we look over time, what happens is you can see that a blast of solar particles come past, a gust of the solar wind, and Comet Encke loses its tail in what's called a disconnection event. So you can just see the material in the tail is swept off into the outer solar system. And so this is a dramatic instance of a general principle, which is that the tail of a comet is caused by particles and gas being swept backwards away from the sun. So a comet's tail will always point roughly away from the sun. I've already mentioned an orbit. Here's a typical orbit. This happens, which one is this? This is in fact Comet Halley, the most famous of the comets. And you can see the comets are characterized by this elliptical orbit. They're not, most of the planets sit on near circular orbits. Comets have this wide variation. And in fact, Halley comes all the way in from the outer solar system, and it comes around roughly every 75 years or so. So it was last visible well from the Earth in 1986. Anyone see it then? I did at the age of about 6. It was deep. Was anyone impressed by it in 1986? A few people are nodding. Roger's shaking his head. The astronomers weren't impressed as far as I can see. It was a rather poor return in 1986. So just because Halley is the most famous comet, it doesn't mean it's the brightest. In fact, in 1986, it didn't come very close to the Earth. And so we got a very poor view of it. And in 2061, the next return, it's even worse. So you have to wait until the middle of the 22nd century, so beyond even the Martin School scope, Ian, to get a decent view of Comet Halley. But this visit into the inner solar system in 1986 proved an irresistible target for those who build spacecraft, for engineers and for agencies who want to explore the solar system, as well as the scientists whose job it is to create ideas for them. And there was something of an interplanetary race to get a probe as close to and to get the best views of Halley during its passage through the inner solar system. There were Japanese probes which headed to the comet. There was an American probe repurposed at the last minute to do a relatively close flyby. But the probe which made the most significant discoveries was a European one. And it was a probe called Giotto, named after the painter whose representation we've already seen. And this is an artist's impression of Giotto. This was a small probe, but one with an audacious mission. Its plan was to fly as close as possible to the comet nucleus while still surviving, to collect particles in situ and analyze them as best it's could to understand the composition of this coma, hopefully to come out the other side and survive, but also to obtain the first decent pictures that we'd had of the nucleus of a comet. So normally if we only see the atmosphere, what we want to see is what's deep inside. And Giotto was a spectacular success. I think for many people involved in European space science, it was a big deal to have won a race, a competition. You know, there's obviously friendly collaboration among scientists, but this was an international competition in which Europe produced the best results. And the results were spectacular. And here is a picture of Comet Halley's nucleus, as seen from Giotto. So what are you looking at? Well, you're looking at something that looks remarkably like a potato on a bad day, as far as I can see. But you're looking at an irregular mass of soot and ice. So the assumption before Giotto's mission had been that comets were sort of dirty snowballs, balls of ice, primarily water ice, but other chemicals as well, with a little bit of carbon and carbonaceous material mixed in. Halley almost reversed that perception. So this is a snowy dirt ball. It's a very dark picture, to the extent that if you go back and watch the footage of the live television commentary, including Patrick Moore and friends covering this encounter, they're deeply frustrated because they can't see anything in the first pictures that looks like a nucleus. They're expecting the nucleus to be bright, and yet here it is, this dark blob, and this is a later processed image. And you can see there's activity. So you can see in that top left corner, that bright area is an area of activity, presumably a plume of material being released from the comet as it's heated by the sun during its close passage. This is a spectacular image. During the year, so this is 1986. In the years that followed, there were a few other small missions to comets. Giotto, having survived, was repurposed, and though its cameras didn't work, visited another comet. The Americans produced a wonderful mission called Deep Impact, where they essentially fired a cannonball into the otherwise inert surface of a comet while it was further out from the sun, and then studied what was thrown up. So you create an artificial site of activity. Actually, I need to correct that. I said that they fired the cannonball in. They were sued in a court in Florida for interplanetary desecration by people who believe they should protect comets. And NASA's defense, although they would have had other legal defenses, I'm sure, was that actually they just placed the cannonball in a particular place in space and the comet ran it over. So this is an excellent example of relativity. So Deep Impact was fun, but it was, to my mind, a sort of lab experiment. It's controlled, we knew what was impacting, and it told us something about the surface of that comet, a comet called Tempel 1, but it didn't tell us about a comet in its natural habitat. And in particular, these are the most changeable objects that we study in astronomy. It's what makes them so frustrating for amateur astronomers, because you can never predict how bright a particular comet's going to be or what it's going to be like as it comes into the inner solar system. And so studying them with flypasts and with one-off experiments is somewhat unsatisfactory. What we want is to be able to watch the whole sequence of events evolving. We want to visit a comet early in its journey into the inner solar system so that we can see what the nucleus looks like before it becomes active. And then we want to watch it develop and change over time. And this was the obvious next step, even after these pictures had come back from Giotto. And so planning started in earnest on both sides of the Atlantic for a mission that would allow us to do just that in the late 1980s. It was actually a rather ambitious program that was conceived at first. So what you want to do, as well as taking pictures, what you want to do is analyze this material that's thrown off. I said that chemistry plays an important role. And so what we want to do is analyze this gas as it comes off the comet, and perhaps even the gas from the surface of the comet itself, or the solid material on the surface of the comet itself. And so the original plan was to go to a comet, grab some of the material, and then return it to Earth. Something that's been done by a probe called Stardust, but Stardust collected only a few thousand dust, or a few tens of thousands of dust grains from the surroundings, not from the nucleus itself. And so this was a very ambitious program. But two things happened early in the 1990s to change that plan. One was that the Americans decided that they had other priorities, leaving Europe to deliver this mission on its own. And the other thing that happened was that the technology of instrumentation advanced. Between digital technology and some clever engineering, mostly by groups at the OU, led by people like Colin Pillinger and so on, they were able to miniaturize a chemistry lab and put it onto the probe that goes to the comet, thus removing the need to bring bits of the comet back to Earth. If you can take your laboratory to your field site, you don't need to bring samples home. And so we ended up with the mission that was to become Rosetta, a mission to travel to the outer solar system, to go into orbit around a comet, and then follow it in, taking chemical analyses on the way and putting that lander, which was to be called Philae, onto the surface. So after about 15 years of planning, launch happened in 2004. This is the actual launch of Rosetta from Kourou in French Guiana. Everything went well, but it takes a long time to get to the outer solar system, not because it's a long way, but because you have to do a complicated series of maneuvers to match your spacecraft's velocity and in fact the direction of travel with the comet itself. So it's not enough just to get to the outer solar system and fly past. You have to do a series of planetary flybys to match your orbit to the comet. That's what they did. There was a nasty period in which Rosetta was in the outer solar system. It relies on solar power. It's a European mission. We don't believe in launching the nuclear material that the Americans use to power probes in the outer solar system. So uses solar power. So in the far reaches of the outer solar system, beyond the orbit of Jupiter, Rosetta had to go to sleep for most of a year. The feeling, I get nervous when I turn my computer off. I have to turn it back on, and it takes a while to boot up. And I know the team were nervous, but things worked, and we soon got our first view of Rosetta's target comet. It's a comet called Churyumov-Gerasimenko. Here's an early view of it, and you can see it's an irregular shape. You can take your pick. It was called the rubber duck for a while. That proves kind of useful because you can talk about the head of the duck and the neck of the duck and so on. Other people claim to see the alien from the Alien films in these images, or there's been a competition online to find the potato that looks most like this comet. And after a year or so of trying, we've got some pretty spectacularly comet-like potatoes. It's irregular as we expect, and it was picked for two reasons. First and foremost, it was picked because it was relatively easy to get to. There was a trajectory that got Rosetta there within 10 years, which is rather fast compared to some of the other possibilities. The second reason is that it's from a family of comets that's different from Comet Halley. So Comet Halley is what's called a Jupiter period comet, and its origins, as I might go on to discuss, lie in the Kuiper belt, the region of the outer solar system where all sorts of rubble like Pluto exists. It's the leftover building blocks of the standard planetary formation processes. Churyumov-Gerasimenko is from the Oort cloud, the vast reservoir of comets that we think lies a good fraction of the way towards our nearest star. And so we think that it represents or near pristine material, which was relatively unaffected by the processes which led to the build-up of the large planets in the solar system. So it's a chance to touch a sort of interplanetary fossil. It tells us about the earliest days of our solar system. And so that's why it's interesting, if only one could go down and work out what it was made of. Here's another early shot, which I rather like. This is being called an interplanetary selfie, though I've got into semantic debates with people about exactly what the word selfie means. We can do that during the questions, perhaps. This is the shot from Rosetta. You see the solar panels, and there's the cometary nucleus in the distance. And you can see they're just about beginning, this is about a month before landing, there are beginning to be signs of activity. And in fact, in this case, you see a jet coming from the neck of the comet. And Rosetta orbited and traveled around the cometary nucleus to provide a sense of where Philae should touch down. And this is a fairly typical picture of the region that was selected. So this is what flat ground passes for on the surface of Churyumov, Gerasimenko. You can see it's a sort of interesting landscape. There are flat areas, but there are also these boulders, which caused slightly early consternation amongst the science team. We're not quite sure how these boulders would form. They turn out as well to be fluffy. So it's tempting. One of the problems with going to a comet is that you look at an image like this and you interpret it with your terrestrial eyes. We're used to reading this as if it's a terrestrial landscape. But these are not solid rock. These are probably 70 to 80% porous. So think like a loosely packed snowball on a scale of a few meters, things like that. Trouble if you land in them, but at least not lethal. And then you have these plates and this slightly strange terrain that we'll come back to. Now, Philae's landing was to be somewhat traumatic. The long cruise into the outer solar system meant that the weight restrictions on what could be carried were incredibly stringent. And that meant there was no room for a powered descent. So Philae was to have no control of itself as it fell down. You literally just dropped the thing. And I think this is the first thing that captured people's attention. It's rather like, and the numbers sort of work out, if you imagine being in a 747 flying over a town and trying to push out a washing machine with an accuracy great enough that it would land on a tennis court. It's that sort of engineering feat that was attempted. And it turns out if you understand that that's what's going to happen and that you're going to have this 7 hours during which time your washing machine will slowly fall, it creates a very tense situation for all involved. And when that tension is released by the successful announcement of a landing, people go somewhat crazy. And it's best if you do that on national television. So this is the moment where we were told that's myself and my co-presenter, Maggie Adair and Pokop, we were told that Philae had landed, but it soon became clear that things weren't that simple, as you might remember. This set of images was released later, and you see from the bottom left to the middle at the top, you see the small triangular shape of Philae rotating but falling towards the surface, and its successful touchdown on the surface of a comet, the first probe ever to land on the surface of a comet. And then over to the right, you see Philae heading off into the distance. Once this was disentangled, ESA announced that they were very proud to have landed on a comet not once, but 3 times. Because what had happened was that Philae had bounced. It was designed to have 2 sets of things happen. One was that it had a little thruster on top, so it did have a tiny amount of fuel, which was designed to be triggered upon impact to hold it to the surface, while 2 harpoons, and they really do look like harpoons, were fired into the icy surface and reeled in so that it could cling to the surface. It was clear from the day before release that that thruster was broken. Or, well, either the thruster was broken or the meter that told you whether the thruster was broken. So one or the other. There was some talk at the time of delaying the release, but they decided to go for it anyway. And the harpoons didn't work either. And so Philae was deprived of the 2 systems that were designed to hold it to the surface. and it headed upwards and started spinning across the surface of the comet. We can actually look at this in a wider view. I don't know how visible this is from the back, but you can see in yellow the dots are the touchdown points on the head of the duck that we're landing on. It touched down again, took off again, touched down again, and seems to have tumbled to a resting place. I think it's a testament to the spacecraft builders that the thing still worked. And we started to get back images like this. This is a confusing image, but this is our shot from the surface of the comet. In the bottom left, you've got Philae's leg. And to make sense of this, what you have to realize is that Philae is propped up against the wall of a cliff at the bottom of at least a small hole. And so what you're seeing here is this is sort of the wall of that hole with perhaps another wall in the far distance. So an interplanetary hole-in-one after a few bounces, but a rather awkward circumstance for a lander that was designed to be flat. Nonetheless, the instruments on Philae could get to work. And at this point, some serious negotiation began. Philae had a number of scientific instruments on board. Each of them has its own requirements for power, for bandwidth to communicate results back to Earth, and indeed just for time, given the limited lifetime on the surface. Philae was designed to last, in the first instance, for 60 hours on the surface, with sunlight coming into its solar panels. It's in a hole, we knew it wasn't getting much sunlight, and so discussions, shall we say, broke out amongst the teams as to the tactics that should be taken. Some of these discussions, slightly strangely, took place on Twitter. So many of the instruments had, and SD2 and MUPUS are example instruments, started talking on Twitter about whether they should be allowed to operate. And much of the discussion in particular was about whether to prioritize getting scientific information in situ or to try and do dramatic things that might release Philae and get it to land vertically. So in particular, there was a drill on board, and there were people who wanted Philae to use its drill to push against the wall and push itself down. And they had a hammer on board. That's what MUPUS is, it's the hammer. Here it is on a schematic of the diagram. And MUPUS was designed to hit the surface of the comet. And they left it to the last minute because it was felt this might destabilize the whole situation. But I like the MUPUS story because they were the first team to get solid scientific results out of their work on the cometary surface. The point of the experiment was to test how hard the surface was. And so you do this by you hit the surface with a carefully controlled force. They did that and they bounced off. So then you turn up the dial and you hit with a harder force and they bounced off. And they tried their third and final setting and bounced once more, thus discovering that the comet's surface was harder than they anticipated. But it turns out they'd programmed in a mode 4, which it's not clear whether people knew this existed. But nonetheless, they had a secret mode 4. They deployed mode 4, which was an even harder hit, and they broke the hammer. And so this tells you exactly how hard the surface was, and it's harder than expected. Not very hard, it has to be said. This is not a very powerful hammer. It's something like the kind of sandstone that you could work a finger into. But nonetheless, this is supposed to be a fluffy mixture of ice and sooty material. This is somewhat confusing, and I don't think we've quite resolved what was going on. Another experiment that happened to produce results early is called CONSERT. Now, CONSERT is actually an instrument on Rosetta itself, as well as on Philae, and the two talk to each other. And the idea was that as Rosetta orbits the comet, the two would send signals to each other through the body of the comet. And in doing so, you could determine the internal density of the comet itself, rather like seismologists use earthquakes to study the interior of the Earth. And there's obviously a question looking at this nucleus, whether this is one body that formed together, or whether we're looking at two separate bodies with rather different properties that have combined, presumably long ago in their history. And so CONSERT was designed to help us do that, but it was pressed into service as a triangulation service. So by recording the strength of the signal, you can work out where Philae is. And although we don't have any images from above of Philae on the surface, we now have a pretty good idea where it ended up, to within maybe 150 meters or so. And the fact that we can't see it tells us that it's deep in a hole. At which point, Philae's signal began to fade. I was in the back of mission control as we could see there was a graph of power versus time, and its batteries literally ran out. It's exactly the same feeling I have when my iPhone starts to die, but on a much grander and important scale. And it was a very emotional moment, I think. We were talking to people all over the world, myself and a few journalists, and you could feel, partly because there was an excellent job done of telling the story of this lander that survived its 60 hours, people were very upset to see it go. The good news is that it got all of the data that it collected off and back to Rosetta and hence back to Earth. So there was nothing lost from its time on the surface. If it gets enough sunlight, it will wake up. And the last calculations that I've seen suggest that it will wake up in late May or early June, that it's getting enough sunlight to keep itself warm, and that as the comet continues its journey towards the sun, doesn't reach perihelion, the point where it's at its closest to the sun until August, it will indeed wake up. And Philae will send us back new measurements, which will be tremendously exciting. But I didn't want to leave the story there because a lot has happened since those few days in November. One of the things that's happened is that the comet has woken up. So here's a close-up taken actually a few months ago now, just at the turn of the year, showing that a jet of material emerging from the neck of the comet. And that seems to be the site of most activity, at least to begin with. But meanwhile, despite the fact the comet's waking up, freed of Philae and its need to monitor the situation, Rosetta has been working its way closer to the comet. So it's gone from this relatively stable mapping orbit, 26 kilometers out from the surface at the start of February. In the last few weeks, it's made some orbital adjustments, burning fuel, of course, to do this. It headed out to take a long-range view, and then just in the last week or so, headed into its closest approach to the comet, 6 kilometers from the center on the 14th of February. And it then headed out and it will resurrect itself back into a mapping orbit. And the idea is to stay as close to the comet as it can until the comet's activity becomes too much for the probe. Those large solar panels, each the size of a tennis court, act as sails. There's a perceptible pressure from the gas being given off from the comet on the sails. And so it's having to behave rather like a decent yachtsman and tack and sail its way upwind. And at some point, when the onrushing force becomes too much, it engages panic mode, runs away to 100 kilometers and calls for help. We hope that that won't happen too soon, because the images we're getting about are spectacular. The comet's surface has been mapped. There are several distinct sections marked by their geological surface, each named after an Egyptian god. The mission team have done a very good job between Rosetta, Philae, and all the instruments. Osiris is the camera of keeping to a theme with the nomenclature. And we're seeing spectacular structures once again. Here's a recent close-up taken from just 10 kilometers away from the surface. And again, it's hard not to look at this with earthly eyes. I see a sand dune here, but of course there's no such thing. It's that fluffy surface again. A large layer of soot, of carbonaceous material on the surface of the comet. And even when you look more closely, the arrows here point out what seem to be wind features on the surface. So these are places where the surface is being scoured by activity, by winds, by jets from the comet, and there are shadows behind these tiny boulders where material has been protected rather from such activity. I want to emphasize that this is a dynamic and changing place, and the real glory of Rosetta is that we've got Philae for the ground truth, but now we have Rosetta to watch what's happening over time. So the comet's becoming active. You see the neck jets, which are now familiar, but you can see now there's material coming off from the head as well. You can see that very clearly on this image. That's potentially a threat to Philae. I said it would wake up. I said it might wake up. I said it should wake up. Of course, if the comet becomes much more active, anything could happen. And people have been forgiven for having fantasies about Philae being jetted out of the hole in which it's landed and returned safely to the surface of a comet. Maybe not that ridiculous. Here's a similar pit seen from above. On the left is an older image. On the right is the most recent one. The illumination is a bit different, but you can see clearly that pits such as this are a source of evaporating material, a source of material that ends up in the coma. And in fact, probably the most surprising result so far has been looking at dust. And these are dust particles collected by one of the instruments on Rosetta. And they found much more dust than expected. And the dust particles that are hitting Rosetta as it flies around the comet are disintegrating. They're hitting Rosetta, not because they're hitting Rosetta particularly hard. They're traveling at about something between 1 and 10 meters per second. So anything from walking to Usain Bolt kind of running pace. But as they're doing so, they're splatting, they're disintegrating, suggesting that they're not icy, they're not held together as solid ice particles. They are, in fact, mostly dust. And we think that what's happened is that on a previous visit around its previous visit around the Sun, the gas from the top layer, the ice from the top layers of the comet nucleus has sublimated, has turned into gas, produced a nice tail, but has done so as the comet retreats from the Sun and left behind a layer of just the dust. And now it's coming back in. It's the dust that's being expelled first. And this is excellent because the composition of these particles matches what we see spread throughout the solar system as interplanetary dust. In fact, it's the source of what's called the zodiacal light, which is sometimes seen as the glow of dust in the solar system. So we now have tied together a comet with the dust that we see everywhere. And so we can begin to piece together the history of the small particles in the solar system. The other result I wanted to talk about was the famous one. Many people in the media, like me, made a big play of the fact that the point of Rosetta was to test whether Earth's water could have come from comets. We have this problem that the early Earth was very hot, and any volatiles, any water or other volatile compounds would have presumably evaporated back into space. And so you need to repopulate the Earth with water. And comets, being large lumps of mostly water flying around the solar system, seem like a good candidate for that. And it was suggested that comets like Churyumov, Gerasimenko, which come from the Oort cloud, which come from the outer edge of the solar system, might well be good candidates. And it turns out there's a test you can do, because water comes in two types. In fact, hydrogen comes in two types. Normal hydrogen has a proton and an electron. But you can also have heavy hydrogen, known as deuterium, which has an extra neutron. And you can make water out of deuterium just as you can water. So you can have HDO or even D2O, just as you have H2O. And the ratio between water and heavy water is a sort of characteristic fingerprint of the origins of that liquid. And so if Earth's water came from comets such as Churyumov, Gerasimenko, the two should match. And we can test this really easy. There's a chemical laboratory on board Rosetta, which goes by the decidedly unromantic name of Rosina DFMS, which is not as catchy as some of the other instruments. So here's the data. The blue point on the far left is, on the left here, you've got the deuterium to hydrogen ratio in water. Earth, you see on the left, there, the blue diamond. I see that I've actually got the comets the wrong way around, as none of you told me. So, of course, Halley's from the Oort cloud, from the outer solar system. It's Churyumov, Gerasimenko and friends that's from the Kuiper belt. My apologies. Thank you for not correcting me. People in the audience who I know that. I'm looking at least 3 of you right now. And you can see that the Oort cloud comets, the distant comets, don't match. Other comets in the Jupiter family, these ones from the Kuiper belt, are pretty close to the Earth. But Churyumov, Gerasimenko is way off. So comets like this one did not supply the Earth's water. But there's plenty more to understand. We shouldn't only care about comets just because they might supply things to us on Earth. We now know from the instruments that Churyumov, Gerasimenko has a very complex organic chemistry. And the results, particularly from the Ptolemy instrument, which is the British-led instrument that took samples of the coma very close to the nucleus, will help us understand exactly what that is. And I'm eagerly awaiting their papers. They must be sitting on their data right now, trying to work out the nuances of what they're seeing. I know that they got good data from the time when Ptolemy was sitting on the surface of the comet. And so, as we were sitting there bemoaning the death of Philae, I'm feeling very sad about our little robot explorer's untimely end, the science teams were cracking open champagne. There is a long tradition, by the way, of comet wine. So great vintages, particularly in the 19th century in Bordeaux, were always bottled in specific, which were marked by comets in the sky, were bottled appropriately. And so this is Filet champagne provided by the concert team. And the science teams had enough data to keep them going for years. And I've touched on some of the first results. In the meantime, I think the other legacy of Philae, which was represented in these rather wonderful cartoons by Issa, who understood that if you put a face on something, people care about it more. That sounds deeply cynical, but it was very well done. That this was a European triumph. And I was very struck by this. It was an interesting, given the political climate, to have an unambiguously European triumph in the field of space exploration, which involved international collaboration and indeed funding across national borders. What was interesting is that I'm not sure that that message got across to everyone who was interested. I spent a lot of time in the following weeks and months with people asking me about the NASA probe that landed on the surface of a comet. This was perceived by, not by you were obviously interested and were paying close attention, but it was perceived by many people as another space triumph, and space is something that NASA does. And so it was surprisingly difficult to get across the idea that the Europeans had taken on a very difficult mission. That's been done before, but also a very sexy mission, a mission that involved adventure and exploration and a series of world firsts. And I think for those of us who talk about this stuff in the media, to audiences and online, our challenge is to point out that we as a European community can actually do this kind of thing, given the right support. That's where we are. There'll be lots more to come from Rosetta and from Filet as the data is analysed in the next few months. I hope I get the chance to come back and talk to you about it. Thank you. Fine, Benny.
So thanks very much, Chris, for an absolutely fantastic introduction to this for those of us that aren't experts. And I'm sure for those that are, there's plenty of points to bounce off. But I can see why you've got the job of presenting the sky at night. You do it so fantastically. Let's open up to Q&A. Who would like to go first? Identify yourself. This is being filmed and webcast, so if you don't want to be on film or webcast, I suggest you don't put up your hand. Yeah. We'll just wait for the mic.
Sorry. Christopher Jenkins from Abingdon Astronomical Society. Will Rosetta survive around the sun?
It's a good question. It's hoped that it will. So obviously things get hairier as the comet becomes more active. It's not essential that it does, but it would be wonderful to be able to see the aftermath as well as things get quiet. The determining factor is really how much fuel it's got left, because I don't know if you can see in the orbital animation that I showed, when there are nice stable orbits, like this round one, a few tens of kilometers away from the nucleus. So this orbit right now, the circular one, can be maintained with relatively little use of fuel. Once you start going further away, the reason it makes this very unspacecraft-like path with lots of turns is because there isn't a stable orbit out there. So it requires fuel to maintain position 100 kilometers away from the comet. So the longer it can stay close in, the better the odds of it still being alive and fueled as it comes around the sun. If it has to run away and engage panic mode early, then they'll burn that fuel before they get to perihelion. The two reasons, as well as the observations from Rosetta, we can't hear from Philae directly. It always relays via Rosetta. And so we need the mothership to stay alive if we're going to hear from the fridge on the surface of the comet as well.
Right at the back.
Yeah, how many times has the comet been around the sun, and the solar radiation it's received, and has that influenced the amount of deuterium on it?
So the comet will definitely have been changed by its previous passages in the fact that we see this dense layer of relatively gas-poor material, volatile poor material on the top shows us that. One of the reasons to like this comet as a subject for study is that it's believed to have remained in the Kuiper belt until relatively recently. So I believe the estimate is that it's been on this sort of orbit for maybe 20 or so previous passes, which is relatively few for one of these comets. Will that change the deuterium to hydrogen ratio? There will be some change with processing over time. One of the things that happens is that the heavier molecules, so those involving deuterium, are more likely to stay on the surface and slightly less likely to evaporate, but we can understand that very easily. And so there's a lot of modelling that has to be done to take that into account, but those are well understood processes. They're things that we can simulate in the laboratory in particular. And so my astrochemical colleagues are confident they can account for that.
Let's just work our way forward from the back.
You better identify yourself and then come.
Hi, Chris. John Zanecki, ex-Open University. Thanks for a great talk. It was lovely to see some of the old images from Giotto, which were very nostalgic.
I didn't know you were around in the 14th century, John.
Touché. You showed that wonderful first image of a nucleus from Giotto, and I'd just like to, there it is, yes, reinforce how important that was, because up till then we had never seen the nucleus of a comet. So, and there were still some people, some respectable scientists who didn't think there was a nucleus at the centre of a cometary coma. So we have gone in, 30 odd years, not very long, from that first image to now seeing the sort of details which you showed us, which I think it's a stunning progress. So I just really wanted to reinforce that.
No, thank you. And John was on the Giotto team, which is why I'm making it. But before you give the mic back, I'm going to ask you a question, which is, I was aware as I was putting this talk together that with hindsight, it looks like there was this sense of competition between the space agencies because everyone wanted to go to Halley. And I've certainly felt that the reason why ESA was so committed to Rosetta, apart from the wonderful science, was a sense that the Europeans owned comets, that it was something we learned. Did it feel like a competition at the time?
Oh, yes, it did very much. And Giotto, I think, was very important because it was the first time that Europe had done something really important in space, essentially on its own, and we did it first and we did it best. And so, yes, there was a sense of competition. But interestingly, this was still the time of the Cold War. There was actually cooperation between ESA and the Russian Space Agency. And it was, you could see signs of glasnost and cooperation, which, of course, now, well, up till a year or so ago, we took for granted. But then that was a big deal. So that was a competition. There was some also interesting sort of geopolitical aspects.
Great, thank you.
Is there a hand sort of somewhere? Yeah, that's right on.
Thank you. I'm Martin Roos from Light Curve Films and planetary scientist as well. Thank you, Chris, for a very nice talk.
Thank you.
I was very intrigued by your very last statement about the fact that so many people thought, apparently, yes, that it was a NASA mission. And I just want to ask you and perhaps the whole room, I mean, ESA really did a lot of work on the public outreach for this particular mission and the landing, and it even made I wouldn't say multi-million euro film, but it put in Lord Baelish from the Game of Thrones in Iceland, talking about comets and things like that. What could we do in Europe to, pump up our profile in a way, if you want? What is your opinion about it, and what do people in the room think about that? And it's very important, I think.
Yeah, no, thank you for the question. No, I think it's important to emphasize, I'm not saying that ESA did a bad job of publicizing Rosetta. I think actually they got more right this time than they have done in a long while. And the cartoon is not there by accident. I think the way they told the story with Philae and Rosetta were tweeting to each other, for example, which sounds silly, but is a fascinating and wonderful way to engage an audience. So I think they did get a lot right this time. I think there are a couple of lessons that can be learned, though. One is that these things are habit-forming, right? That it's not enough to do a good job on the publicity this time. It just has to be always good, and NASA are great at this. So, you know, when anything lands on Mars, you have the shot of scientists whooping and celebrating, and, you know, polite handshakes around the conference table don't work so well, and we've established that. You know, I think just a few months before, we had the first serious data release from Planck, which is an ESA satellite that studies the very early universe. It is providing the definitive picture of the first light we can receive from the universe's history. It's a fascinating story, and the results were announced literally from a press conference with 9 old guys with ties sitting around a table in Paris, talking at quite technical detail. You know, ESA's often got this stuff wrong, and it takes time. The second thing is that I think openness is becoming increasingly important. So sharing the products of the mission, not just the story that you want to tell, but allowing people to explore, I think is hugely important. I was very struck that a lot of the images I wanted to use in this talk, this one with the labels on, for example, come not from the ESA website, but from the efforts of volunteers who've taken the raw data and processed them in a way that the scientists don't have time to do, to create aesthetically pleasing or storytelling images. Now, there's a wealth of Rosetta data from a camera called Osiris. Almost everything I've shown you is from a low-resolution navigation camera. There's a high-resolution camera on board that's produced spectacular images like the shots of Philae descending to the surface. Those images are in the control of the science team and not shared with the world yet. There are questions of scientific priority, but I think if we can learn to be more open, and if we can adjust the way we do science to be more open, I think that will help immensely. And in Europe, we've been slower to learn that lesson than in America. Soapbox, that's the end of the soapbox, but I think all of that's important.
David Woodward, Shropshire Astro Society. Watching a lander bounce must have been an unnerving experience. What is the escape velocity of the comet, and how close was Philae to exceeding that?
I used to
maybe also translate the question.
Yeah, of course. So the escape velocity is the speed you need to go to escape from a body, to no longer be bound to its surface. I'm trying to remember the number for the Comet. I certainly think that if you ran, you'd escape. So one has to, if you're ever on a Comet, walk slowly. That's the first thing. What I do know is that slightly terrifyingly, Filet reached 80% of that velocity on its bounce. And so had the Comet's surface been a little different, had the impact, had it landed somewhere else on that landing site, it may well have disappeared into space forever. Which would have been rather upsetting. We would have got a little bit of data because it was, as it bounced, it continued to believe it was on the surface. So it carried out its program of scientific experimentation as it was bouncing. And this is actually being used. So the chemical analysis, which was designed to take place on the surface, now gives us a nice cross-section of the first few kilometers of the coma. And so we could get useful information from this. But it was a very, very close run thing. There's a fascinating, if you go back and watch the video, you can see there's a point where they announce that it's on the surface and everyone starts celebrating. And in the back corner, there's a young postdoc looking at a screen who looks incredibly worried. And what he can see that no one else has noticed is that the thing is rotating. And so for a while they believed it was both on the surface and rotating until another obvious explanation came to mind. And then we had the long wait to see if it was going to transmit a signal after it had bounced. And we got a signal just about half an hour before the end of the day where Philae was. And so then we had to wait overnight to see if it survived, had a second day of science, and then on the third day, the batteries ran out, but only after the science was completed. It was incredibly nerve-wracking and incredibly exciting. I mean, for a press and PR point of view, it couldn't have been scripted better. It was just absolutely wonderful, but I'm not sure I would have wanted my career to be on that bounce.
Back there, yeah.
Thank you. Gurinder Pant from ISIS Innovation Limited. Question I have is, can you calculate the mass of the comet before the tail appears? Can you then calculate how much mass is being lost as it goes around the sun, and therefore how long the comet is likely to last as a whole?
Yeah, that kind of calculation can be done. I mean, I can't, but that calculation has been done. In fact, we can do that from Earth rather well, so that can be understood. I can give you a general answer, which is that Jupiter family comets like this, if left alone, last, I'm looking at the experts in the room, thousands of times around the sun. But what normally happens before then is they have a close encounter with one of the large planets, which throws them off their orbit. So it's more a dynamical limit to how long they survive in the inner solar system, rather than the comet running out of juice, as it were. Although that's one of the questions that we didn't really understand that we now do, is why doesn't the comet just evaporate entirely on one pass? What is the mechanism by which the comet survives? And again, I think this dark layer of material on top that we seem to think has evolved, which seals a large part of the ice underneath, will be the answer to that. So the comet is almost self-regulating in that sense. And I think checking the details of that will be an important part of the rest of the mission.
There was a previous comet which a lot of fuss was made about it, but unfortunately as it went around the sun it just...
Oh, this is Comet Ison, so this was a year or two ago, which was going to be, if it had survived its passage, would have been a really spectacular comet in the night sky. And I saw it, I was privileged enough to see it just after sunset, and it had a beautiful tail already, and then it disintegrated. So comets don't always survive. There's a large class of comets known as sun grazers that commit suicide runs straight into the sun. These things are transient, and it's why watching them change is so important, and trying to understand the evolution of this family of comets, and of comets in general, it's critical if you want to understand them. You can't just build much on a snapshot. You need to watch what happens over time.
Okay, let's walk down. Yeah.
Hello, I'm Andrew Kay. I'm an Oxfordshire resident. You showed on the picture that the comet is giving off its tail from the neck part. Why is it the neck part?
Yes, that's an excellent question. I have only speculation. There are contradictory papers on this in the literature already. The thing I'm waiting to find out, which will help answer that question in a satisfactory way, is whether these are really two bodies or whether they're just one. Because if that's a join, you can imagine that it might be structurally weaker. There are close-ups that I don't have in this slide deck that show cracks appearing. Again, I am no expert in this, but the story that seems to make sense to me is that this is a relatively weak area of the comet, perhaps because it's a join between two bodies, or just that it's been eroded away and it's cracking. Another set of hypotheses is that dust moves around on the surface of this comet. We see that in the wind streaks that I showed you. If that's true, then it's possible that darker material would gather at that neck. It would be sort of a trap for the particles as they move around. Darker material absorbs more sunlight, and so that there may be a temperature distance as well. There are instruments on board Rosetta that will help distinguish between those two, but the scientists who have the unenviable task of both flying the spacecraft during these dramatic maneuvers and trying to write up their results from the most important experiment of their careers at the same time haven't quite got the pieces together yet.
Hello, I'm Andrew Filet. I'm a member of the school. I'm an economist, but I enjoy these sort of things. My friends thought I was mad staying up watching this live in the middle of the night. What's that all about? You relied on two critical pieces, or they relied on two pieces of technology to pin it to the object, and both of them failed, but they must have both been tested for takeoff, vibration, radiation, all the rest. What's the latest on why they didn't work, and would you design the thing differently in the future?
Well, I certainly wouldn't let me design it. Let's be clear about it. And I don't think we yet have an official report on either of those failures, but somebody will be looking at it. The one thing that struck me was that they were both mechanical failures. So the thing that went wrong with the thruster was that you have a tank of fuel and then the thruster itself. You have a membrane between the two, and just before you're ready to use it, you want to break the membrane and allow the fuel to flow. And so rather than have a shutter or something like that, it had two pins which were supposed to come down and pierce the membrane, and there was a redundancy because either one of them could have done so. It appears that neither operated, so it's a mechanical failure. The harpoons, again, it seems to have been a mechanical failure of what moves, and I suspect that the answer is that 10 years in deep space is rather hard on your equipment. You can update software. There were software glitches on the mission. There are on every mission, but people were able to send new commands, and in fact, the software on Philae was upgraded 4 days before landing, because you can work on that while you're in space. The mechanical stuff is harder, and I suspect it was wear and tear after a long cruise. Whether you would have done anything differently, it's easy now. If you know what's going to fail, you would have put redundant systems on, but you can't do that for everything because you don't have the weight. So I'm not sure. I think it may well just turn out to be one of those things. There's certainly no way we could have flown something with a powered descent. That would have just been too heavy. One thing that I have seen commented on, which I have more sympathy for, is the fact that there's no doubt in my mind that if this had been a mission in partnership with NASA, we would have used as a source of power not solely solar power, but the kind of thing that powers the Curiosity rover on Mars, which is a small lump of radioactive material that gives off heat, and you can get power from that. They're heavy, but my guess is that if you had a bit of leeway, you'd add one of those, because that would have kept Filet working after the solar powers. These things are always a difficult trade-off, though. I mean, Filet is believed to be currently receiving 3 watts a day, so that gives you an idea of the power budget that you have to work in, let alone space and weight and so on.
Why won't the Europeans allow nuclear?
It's a combination of never having developed the technology, but it's also an environmental concern, because putting plutonium in a rocket which has a known failure rate is not necessarily a good idea. It's very useful, but there are obvious downsides.
Sorry to intervene again, but there actually was another system for fixation which also didn't work, but I think it didn't work because
the screws at the end.
Screws in the feet didn't work.
So as far as I understand, so the other thing was that it had ice screws. You're quite right, thank you, at the end of the feet, which was supposed to screw it. As far as I understand the situation, they worked, but it's no good if you're not held to the surface. So in the early seconds of its bounce, it screwed itself into what passes for thin air. So as far as I understand it, that's not a failure. It's a consequence of the failure of the other 2 systems, that didn't hold it to the surface. I think they were designed to trigger after it hit the surface, not just before. So I think they get a pass for that, but it's true that was a 3rd system that didn't work. But yet it survived. I think that it's very tempting in these things to look at what didn't go right. But the truth is that a working spacecraft was delivered to the surface of a comet, something that hadn't even been attempted before. And there's only one previous example of the first landing on an astronomical body succeeding, huygens is the Huygens probe on Titan. But when we first went to Mars, Venus, the Moon, with asteroids with robotic probes, things went wrong. And yet this worked well enough first time to get great data. So I mean, it's interesting to talk about both, but it shouldn't take away from the success of the mission.
Yeah.
Matt Smith, Cybersecurity CDT. Do you think we'll see missions like this again in the future, or is this a one-off?
I hope so. I suspect it might be a while before we go back to a Comet, though. So these missions are selected in competitive bidding. So scientists all over Europe think up proposals and then send them in to fit within a certain budget. So there's a selection going on right now for a medium-class mission, which has everything from telescopes to observe the cosmos to a probe to go to Uranus, through to, I think there's a plan for balloons on Venus as well. There's all sorts of things. So this was a large mission by European standards. It was €1 billion plus the cost of the instruments. Peanuts compared to other spending. It's about the price of 3 decent passenger jets these days, something like that. But it's big money for ESA. And I suspect the attitude will be that we've sort of done comets. But in 20 or 30 years' time, I can imagine what we'd want is a long-lived lander on the surface. I think that's the next thing. other ideas exist, but I think you'd want something that could sit on the surface and send back images from close up as this activity develops. Any good scientific experiment will produce more questions, and I'm sure in a year's time we'll have a list of questions that we'll need another mission to go and resolve.
Chris Bevan from the Wickham Astronomical Society. I'm old enough to remember Patrick Moore on TV when Comet Schumacher-Levy 9 plunged into Jupiter.
Yeah, me too.
And one of the questions he was asked was, what do you think this material is like? And he said, it's like dilute cigarette ash. And yet, as we know, it made a big impact on Jupiter. Was the thinking about comets and their structure and composition at a pivotal point then? I mean, did we really think that comets were all cigarette ash?
Well, I think what you're getting there was the view after Giotto, so we knew that it was this dark material. And one of the other mysteries that I haven't talked about that's come out of this is I talked about the looseness and the fluffiness of the top layers, but it turns out that the porosity of the comet as a whole is very high, so about 70 to 80% of it is air, or is space, rather, because there's no air. So this is a very loose structure, and that's not a bad analogy. Comet Schumacher-Levy 9, for those who don't know, was this fascinating event in 1994 when a comet was seen not as a single nucleus with a coma and a tail, but as a string of nuclei, a string of pearls. And it had been ripped apart by Jupiter's gravity and proceeded to hit Jupiter over the course of about a week. The different nuclei plunged into the atmosphere. And the most extraordinary thing, it happened on the far side of Jupiter as seen from Earth. And as the impact sites rotated into view, there were these enormous bruises in the top of Jupiter's atmosphere, which were visible even in a small telescope. Remember it very, very clearly. And so the idea that something that is this loose, and after all is nothing compared to the size of Jupiter, can have that large an impact is kind of interesting.
Very fast.
Indeed. Well, that's true, and that helps. And there have undoubtedly been cometary impacts on Earth, even if that's not the source of our water. So I think I don't think we've yet found anything that overturns the picture that we had post-Giotto. What we're getting is the level of detail that we need to understand it properly.
Yeah, woman over here.
Hello, my name's Alison Brindle. I work at the university. Will we get to see another comet here on Earth soon?
Comets, there's an old astronomer saying, which is that comets are like cats in that they have tails and are completely unpredictable. And so what we really want is a spectacular comet that's visible in the naked eye, preferably in daytime, with a beautiful long tail. Those things are almost always first-time visitors. And so they catch us by surprise or with a year or two's notice. And so there's nothing that we know of that's coming that's going to be spectacular. But then that doesn't mean there won't be a good comet in 2017 or 2018. So we get a plentiful supply of regular visitors. We get a plentiful supply of comets that are sort of on the edge of naked eye visibility. Lovejoy for astrophotographers in particular has been spectacular. But we haven't had a comet for the rest of us in the northern hemisphere well placed since the late 90s. But it's just chance, I'm afraid.
Great. Anyone else have any questions or comments? We are going to have drinks afterwards, to which you're all invited, so you can try and collar Chris to follow up. I just want to give you some sense of the forthcoming things happening before we say thanks to Chris. The Oxford Martin School has a huge range of activities for those of you that don't know us. I'd encourage you to look at our website. But this next Monday, on the 2nd of March at 5:30 to 7, we have Dame Sally Davis, who's the UK's Chief Medical Officer, speaking about the threat of antibiotic resistance. And that, because we've had so many registered people, will be at the exam schools, not in this venue. On the 4th of March, we have Professor Vlatko Vedral, who's the co-director of our program on bio-inspired quantum technologies, talking about living in a quantum world. And if you don't know what bio-inspired quantum technologies are, it's absolutely fascinating what we learn from nature about quantum. I encourage you to come. On the 18th of May, so in the next term, we have Connie Hedegaard, who's the former European Commissioner for Climate Action, who led the climate negotiations in many massive global theaters like Copenhagen, talking about the inside of the politics of negotiations and the gulf between scientific knowledge and political outcomes. And on the 20th of May, we have Professor Molly John, who's a visiting fellow here, speaking on feeding the world. And then finally, in our exceptional lecture series, we have on the 27th of May, Chris Woods, who's an award-winning investigative journalist, talking on America's secret drone wars. Then we have also, which I strongly encourage you to come, our ongoing Thursday at 5 o'clock seminar series. The theme of this term and next term is climate change and how to stop it. This coming Thursday, following week, 5th of March, Global Water Risks by Professor Jim Hall, 12th of March, Biodiversity, and the series continues on Thursday. So please do come to all of that. Join us for a drink, and let's thank Chris. That's it.